Hello guys, welcome back to the lesson about differentiation, and today we will discuss about implicit, partial, and parametric differentiation. So, after watching this video, you will able to apply the product rule, the quotient rule, and the chain rule for implicit, partial, and parametric differentiation. Let's get started. The first one about implicit differentiation. We will review our chain rule, which dy dx is dy du and multiply with du dx. So when you have y equal 2x plus 1 cube, you will let u as 2x plus 1. So what you have here become y equal u cube. So this is the composite of the functions. Then by using the chain rule, dy dx will be obtained when you differentiate dy with respect to u, and then you continue with the differentiation of u with respect to x. So that for the dy du, what you have in here is 3u squared. This is the dy du. And for the du dx, from 2x plus 1 become 2. So our dy dx is, we substitute back u to 2x plus 1, and we have 3 times 2 equals 6. U squared become 2x plus 1 squared. Now, if we work in different variables, suppose we have z in terms of y and y in terms of x. Here, z is a function of y, and then y is a function of x. So that the chain rule will then state dz dx. If we need to differentiate z with respect to x, we will differentiate z with respect to y first, and then we continue to chain with the differentiation of y with respect to x. For example, here we have z, which is y squared. We need to differentiate this with respect to x. So, by using chain rule, dz dx will be dz dy multiplied with dy dx. In here, dz dy will be 2y, and then you will continue with differentiation of y with respect to x. So in general, to differentiate a function of y with respect to x, we differentiate it with respect to y first, and later we will multiply it by the function derivation dy dx. So here, for the function of y, if we need to differentiate it with respect to x, it will be d fy with respect to y first, and we continue with dy dx. Let's see example 2. Differentiate the implicit function y squared plus x cubed minus y cubed plus 6 equals 3y with respect to x. So now we will differentiate each term with respect to x. In here, we have dy squared. We will differentiate it with respect to x. Dx cubed differentiated with respect to x, and so on. And then, for this, we will have y squared. Since y is a function of x, then we will differentiate it with respect to y and continue with dy dx. And also for here, all with the function of y will be continued to dy dx. So that for the differentiation of y squared with respect to y, we'll obtain 2y, and then we have dy dx. In here, for the x cubed, we will have 3x squared. And in here, we have 3y squared multiplied with dy dx. And in here, we will have 3 multiplied with dy dx. Now, we will collect all terms involving dy dx together so that we have these terms. And we can take the dy dx out backward, and we have dy dx is 3x squared divided by 3y squared minus 2y plus 3. Differentiate the implicit function y squared minus x times y plus cos y equals 0 with respect to x. So in here, we have y square become 2y multiply with dy dx, and minus xy have to apply the product rule in here. So we differentiate x, which is 1, and multiply it with y. After that, we differentiate y, which is become 1, multiply with dy dx, and multiply again with x, and cos y, which become minus sin y, multiply with dy dx. So that after collecting dy dx out, what we will have in here become dy dx is y over 2y minus x minus sin y. The second one is about the partial differentiation. For the partial differentiation, we will derivate function where we hold other as a constant. It is applied in a function of two variables x and y, which is denoted by f, a function of x and y. For example, in here we will have the two variable x and y in the same terms. So for this case, what is the partial derivative if we want to derivate it with respect to x? We will denote it the partial derivative with respect to x as fx, and we partially differentiate f with the variable is x, so that other variables, for example y, will be a constant. So when we treat y as a constant, what we will have here is 2x, because y is supposed as a number and the differentiation become 0. Now, for example, if here we will differentiate it with respect to y, then it will be denoted as fy, and we will partially differentiate the function with respect to y. And the result of the partial derivative of f with respect to y is 3y squared. Now, for the second derivative of partial derivative will be denoted by the first one, fxx. What is fxx? This is the partial derivation of fx, continue derivated again with respect to x, so that it will be denoted as d square f dx squared. And for fxy, it will be a partial derivative of y, which later derivated again with respect to x, so that it will be denoted as d square f dx dy. Fyx will be the vice versa. In here, you derivate f with respect to x first and continue to derivate it with respect to y. And for fyy will be two stages derivative with respect to y. So this is the symbol and also the notation for the second partial derivative. Example 4. Determine all order 2 partial derivative of the function z equal x cubed y squared minus xy to the power of y. Here, for the z dx, so now we will differentiate all the function with respect to x and suppose y is a constant. So in here, if y is the constant, we will derivate x cubed, which become 3x squared. And it is multiplied by y squared, which is just following. And also for xy to the power of 5, since y to the power of 5 is just a constant, then the result of minus x derivative become minus 1, and it will be multiplied with y to the power of 5. Now, if we continue to derivate z with respect to x again, it will be d squared z dx squared, which will become 6xy squared. From this 2 multiplied by 3, and then the y will be constant, and the minus y to the power of 5 is become 0. And next, for the second derivative of d2z dx dy, it will be 6x squared y minus 5y to the power of 4, obtained with having x as constant. So in here, we multiply the constant 3 with 2, which becomes 6. And then since x squared is just following, it becomes 6x squared y. And in here, y to the power of 5 become minus 5y to the power of 4. Next, for dz dy, it will be 2x cubed y minus 5xy to the power of 4. So, what we differentiate in here is y as the variable and x cubed as the constant. So, you will multiply 2 with x cubed and the power become subtracted by 1. And in here also x is a constant. So, what you have is minus 5xy to the power of 4. And with the same way, we also have the second derivative like this. The third one is about parametric differentiation. So, of a function defined parametrically, for example, cos t and also sin t for x and y respectively, it is often necessary to find the rate of change or maybe the gradient. So, you will need to calculate dy dx. So, how to calculate dy dx? From the chain rule, we know that dy dt will be dy dx multiplied with dx dt. By rearrangement, we can have dy dx, which is obtained from dy dt divided by dx dt. Where, in here, since dx dt is at the denominator, it cannot be equal 0. So, in general, to differentiate parametric function, if x is a function of t and y is also a function of t, then you can have dy dx from differentiate it with respect to t and differentiate x with respect to t and divide the result. Example 5. Differentiate x equals t cubed minus t and y equal 4 minus t squared with respect to x. So this is needed dy dx. X equals t cubed minus t can be differentiated with respect to t become 3t squared minus 1. And for y equal 4 minus t squared can be differentiated with respect to t equals minus 2t. So, when dy dx is dy dt divided by dx dt, we can have dy dx is minus 2t over 3t squared minus 1. So, the summary for this differentiation, we have implicit differentiation, which we differentiate y with respect to y, continue with dy dx, and for the parametric differentiation, we have to divide dy dt over dx dt to obtain dy dx, and for the partial differentiation, we can partially differentiate it with making any other variable as constant first. So that's all for today's lesson about differentiation. Let's continue again in our meeting to discuss more examples. Thank you for watching this video until the end. God bless you all. Bye-bye.